Okay, I think we may start. So I'm glad to see all of you in our next scientific webinar. And before we start, I would like to announce the next seminar. The next seminar will be again in the framework of our BRICS project. So Ivan Yakonov from our Quantum Technology Center will give a talk with, and okay, the name of this talk will be announced later. But it will be next week, the same time. And now we have a talk from Alexey Melnikov from Basel University and also from Valiev Institute of Physics and Technology in Moscow. And the name of his talk, Machine Learning for Setting Up Quantum Experiments. So Alexey, please, you may start.
Hello, everyone. Thank you for coming to this seminar. Happy to see so many participants. I hope you hear me well. So how is it, Konstantin?
Yes.
The sound fine. Yes.
Sound good.
Good. Thank you for introduction. Here is the outline for my talk. I will first start with a short introduction with our motivation. Then I will go to two topics of this seminar. The first one is reinforcement learning designing photonic quantum experiments. And in this part, I will give two examples. The first one will be free photon entangled states generation experiment. And the second one would be about violating Bell CHSH inequality. In the second part of the talk, the second topic will be about supervised learning for designing quantum networks. And this part will be about showing how we can do quantum speedup in particle transport. These are three topics, three research projects. The first one is done in collaboration with people from, so it was done in Austria. These are people from Innsbruck, Hans Hendrik, Vedran, who is now in Leiden, Anton in Vienna, and Mario from who is now in Toronto. The second example in reinforcement learning for generating quantum experiments will be about violating Bell CHSH inequality, and it's the topic we are now exploring in Basel with Nicola and Pavel. And Pavel is now here with us on the seminar. And the third topic is quantum speedup and particle transport. It's done together with Leonid in Moscow, Alex. They're both here, I suppose, now on the seminar, and Ray Kong from Taiwan. So let me start with my motivation. I would say for last 7 years, I'm exploring the topic of agents that interact with environment. So this is a very general picture where we have some agent, which can be a robot, or it can be a computer program, it can be some device, which interacts by getting some inputs, perceptual inputs, and doing some actions on this environment. The most interesting part is the part where the agent is actually a learning agent. That means the agent learns from what it gets and what it does, and changes its actions depending on what it saw before, depending on the experience. The question we ask in our research is, what's the role of physics in this learning process, or especially what's the role of quantum physics? And there are two immediate answers that I can give. The first one is, we can say that the learning agent is a physical device, or physical robot, or let's say it could be also human. Let's say learning agent could be a scientist. It can be classical or quantum. So what we can get if we think of it as a classical object, we can think of physics-inspired learning agents. That means we can think of this actual device, how it works, what are the physics, what we can improve to make the learning better according to some measures of our interest. Or this physical object can be a quantum object, and we can think of quantum enhanced learning agents. So agents that deliberate faster, they think faster, they make decisions faster. And this is the first part of the story. The second part of the story is where we think of our environment being a physical object. And that means, again, it could be a classical world, a quantum world, and our actions could be measurements done by the agent in this world, and percepts could be some measurement outcomes that the agent perceives. And I will talk about this situation where we have some learning scientist, learning agent who observes something, does measurements, and repeats it many times. The interesting part here would think of an artificial learning agent, artificial learning scientist in this case, or as we can call it, computer scientist, right? Which actually is programmed to observe physics and manipulate, let's say, objects to learn from the observations. And this direction goes beyond physics laws extractions from data, which is another direction we can think of. For instance, if we gather some measurement outcomes, we can think of, let's say, fitting, do some curve fitting in one way or another using neural networks or not, and then maybe come out with a minimal description of this data and hence come up with some laws of physics from data. This is different. In this picture, we actually get no data a priori. We have to gather this data. So we have to do measurements, we have to do observations, we have to repeat, and this is all decided by this artificial learning science. And this is the framework I will use now in this talk. This, of course, may be a bit philosophical, what is shown here, right? Very, very general, but let's be now a bit more concrete. What could be a machine learning framework which is most suited to tackle this situation of this artificial learning scientist? And one way to approach it is via reinforcement learning, because it's very similar. Let me show what's different in reinforcement. In reinforcement learning, we get states from environment, we do actions, and in addition to that, agent also receives a reward, which is some reflection of how well agent behaved with actions given states. Mathematically speaking, this is we can describe states with time-dependent variables, rewards are time-dependent variables, actions are time-dependent variables, and the whole thing that agent does in this picture, it takes these states S of t and maps them to the actions A of t. And this is done by some fixed function, policy function pi, which is a function of time-dependent parameters of the agent h of t. And as I said, this function is fixed. So what we can change this time-dependent parameters. So we can hence change the way we map states to action. So the whole process of learning in this picture, the whole way of improve the agent would be in designing a learning algorithm which updates these parameters h of t after each time step. To test this idea, to test the idea of reinforcement learning, of learning agents actually contributing to some scientific, let's say, discoveries, just to try to approach this, we decided to deal with photonic quantum experiments. One reason for that is complexity of this experiment. So we can look, for instance, at this optical table, a typical arrangement of elements. It's complex enough. So we might think maybe actually some artificial agent might help us in arranging this element. So let me summarize how we look at the process of creating experiments in simplified way. So first, we define some research goal given existing tools. For instance, we want to create a optical quantum computer, and the tools were given, let's say, are optical tables, linear optical elements, some nonlinear crystals. And with that, we need to find a solution that achieves our goal, let's say our goal for creating a quantum computer. And then we execute this solution in the laboratory. We try to understand what's needed, order things, write programs that talk to different devices, deal with problems, iterate many times until we supposedly reach the goal. What we try to improve with our learning agent approach, with our artificial learning scientists, is the step of finding a solution that achieves our goal. So the agent will be given a target and tools which are available, and the agent will try to find the solution. So what are the usual elements in our toolbox? As I said, it's photon sources, nonlinear crystals. If you go to high dimensions, as we do next, it would be orbital angular momentum holograms, dark prism mirrors, beam splitters, detectors. And we know that if we arrange all these elements that are listed on this slide in a proper way, we can create multi-photon entangled states in high dimensions. So this is known, and there are several examples that were known before we started. So this is the picture how we proceed. We use a certain type of learning agent called projective simulation agent, or for short PS agent, which puts optical elements on a table. And to be clear, this is a program. So we program this agent. So this is like a machine learning package that is here. And this is a simulated physics, which is placed here. So it's not a real table for now. We of course do it all now in a simulated way. And the agent places optical elements. Then there's an analyzer that checks if the experiment is good or not. This is like having, let's say, a head of laboratory who looks at the results of the experiment, and this head is she or he is happy or not about this experiment, and this comes as a reward. So the agent is told, okay, this was a bad experiment, or it was a good experiment. And in addition to that, agent also perceives the current arrangement of the optical table. So I hear some echo, but it disappeared. Yes, so we can look at it also in a way that, in a bit of circuit diagram way. We can think of optical paths. There are like 4 optical paths, A, B, and C, D, and we place some elements like SPDC crystals, some mirrors, holograms, beam splitters, and we proceed in this way until we decide to measure optical path in optical path A and try to achieve a 3-photon state of our interest in path B, C, D. And if we look at that way, this problem would be similar to problem of circuit design, Hamiltonian design, quantum control, maybe some others. But it's not directly the same, as details, as it turned out in practice, depend quite a lot on state space dimension, action space dimension, length of typical action sequences, sparsity of rewards, and some other details. So I talked about the states of interest, that our goal, our target. And in this case, we chose a target of 3-photon entangled states in high dimensions. The question we can ask, for instance, we know clearly how to create a GZ state, 3 zeros plus 3 ones. This is well known, but how to create a state in high dimension, 3 zeros, 3 ones, and 3 twos. And it turned out it's not that obvious. Or if you go further, how to create other states in high dimensions, for instance, maybe plus 3 to 3, plus 4 for 4, and so on. or some maybe asymmetric states. To visualize how all states look like in a Hilbert space, we can look at this diagram where all biseparable states are placed over here. And then there comes 2-2 states, which correspond to a GZ type entanglement. And these three numbers, 2, 2, and 2, are reduced ranks of reduced density metrics, so-called Schmidt rank vector. So these three numbers form a Schmidt rank vector. And if we increase these numbers, go to 3, 2, 2, 4, 3, 2, and so on, we increase the amount of entanglement we have in our system. So we increase, so to say, local dimensions of each individual subsystem. And of course, the interest is to occupy this space as much as possible. So we want to know how to create both 2, 2, 2, 3, 2, 2, 4, 3, 2, 5, 6, 7, and so on. So the more the better. We want to fundamentally explore the space of all these possibilities. And this exploration comes not easy. So let me show you an example. If I put a vertex in this picture, and this vertex corresponds, let's say, to some unique configuration of our optical setup. Let's say this corresponds to an empty table having no elements. Then we can place, let's say, do an action as an agent, do an action to place a beam split in nodes B and C. This would lead to a new experiment. Then we can proceed, get a next experiment by placing new elements and do so on and so forth. But we can also come back because, of course, some elements commute, some elements can cancel out. So some actions can be useless in the end. So these last 4 actions actually brought us to the same experiment that was before. And if I visualize just how complex the space might be, I show here just randomly sampled 45,000 generated experiments. And these big dots that are highlighted are experiments that are potentially interesting to us. They give some 3-photon entanglement in high dimension. So there are only 67 out of 45,000 in this picture. And we don't know like if the 67 actually what we are going to do in the lab. So we want to build a database of much more potentially interesting experiments. And this is only 45,000, which is a tiny sample of all the possibilities. So why would we think of reinforcement learning by looking at this picture? So if I look at this exploration space of all possible experiments and zoom in a bit, take a sample from this part, we found that it corresponds to a scale-free network. So it's not just a random arrangement of experiments. It has some structure. And this structure can be thought of some complex maze in which agent navigates. So agent starts, let's say, an empty table, and agent has to place some element. It moves to another, let's say, room or another experiment. This action actually brings to a different experiment, and so on. And you are like walking in this space of possibilities until you reach some experiment of interest. And this is very similar to a problem of navigating in a maze, which is a typical reinforcement learning problem where we have some labyrinth. Agent is placed in some room, and the agent can go in some of the directions. The goal would be to find the start, to find the exit. And very similar things happens here. The only difference would be that there are many more rewards, and the space is much larger. Plus, we cannot describe it with 4 actions. There are like 40 or 50 actions. So it's there are many more dimensions in this problem, and we cannot possibly visualize this maze. So in this toy problem, you can clearly see what would be the optimal way to reach the goal. But in this space, we cannot even draw a map because there are so many possibilities. Yes, I talked about reinforcement learning, the way we would use reinforcement learning. And the actual implementation of a reinforcement learning agent is projective simulation. I will not talk much about this model, but just for illustration, let's say we have a layer of states. So each circle corresponds to a particular experiment, experiment S1, experiment S2, S3, and so on, until Sn. And these actions, A1, A2, A3, and so on, until A30, they correspond to adding a new element, adding to this existing state. For instance, if we start with empty table, we do an action 4, we end in state S2, and we proceed in this way. It's a random walk process. So we do a random walk. And importantly, this random walk is done on a weighted graph. So these dashed lines, which are shown here, these are, they correspond to probabilities of transitions, Pij, and this Pij depend on the weights Hij. And these weights are changed according to some learning algorithm. So the idea here is that agent starts with a network which have Pij all equal. They are all equal to 1 over number of actions. And then these probabilities are being learned, they're being updated so that the agent ends up with a probability distribution which corresponds to distribution which favors experiments or actions that lead to entangled states generation. So what's the result of running this projective simulation agent? We found out that no matter what limitation we set on the maximum length of this experiment, we always end up having more experiments that generate entangled states. So these are these blue lines, 2 blue lines. More compared to the automated search approach that was used before. So this is more like grid search, random search approach used to find new experiments. And we saw that no matter which Schmidt-Frank vector we choose, it's 2 to 2, 3 to 2, or any other, projective simulation finds always more experiments. We saw one reason that there are many more experiments that were found is that agent keeps learning. So for instance, these red lines, they correspond to automated search. And we see, even though this like improved automated search learns for some time, so with number of experiments, it keeps the fraction of good experiments keeps growing. It saturates really fast. And for machine learning agent that we use, it actually grows. It doesn't saturate it for this 10,000 experiments that I showed here. So we know that the reason would be in that it keeps learning much longer than just automated approach. And on average, we found 1.5 more classes of entangled states with machine learning approach than was known before. On this slide, I want to explain you a bit more details about how reinforcement learning actually learns. And for that, I fix the class of states I'm interested in. I'm interested in only in this 332 entanglement class. And I ask the agent to generate these states from scratch, and I reward the agent from getting these states. So I see that success probability, which is shown here, it grows from 0 to 1. And in parallel, which is important, the length of this experiment goes down from 8, which means that agent actually not only learns to design target state, but also learns to optimize the length of those experiments, which is an internal feature of all reinforcement learning approaches. And another feature of reinforcement learning approach is that if we now switch the state of interest from 332 to 333, then suddenly, of course, success rate drops down to 0 because the agent is no longer rewarded for what was important before. But then it quickly relearns up to probability 0.5 to generate this new states from this class. And the length also drops quite fast. But important question to ask here is what happens if we don't have this phase? So if we from the very beginning ask what will happen if we work 3C3 states, and the answer is learning will be very slow. So this dashed line shows that success rate, success probability is very close to 0. It rarely goes up. Maybe sometimes it goes up, but it's a very rare event. That means that agent actually exploits the fact that if you learn states to generate states from one entanglement class, then you achieve better results for another entanglement class. And this is a picture that shows how the maze, the complex maze looks like, a sample of it, a small sample of it, if we explore the space with reinforcement learning. And we see that rewards are very much clustered in some regions. That means they're related. All experiments that are of our interest, they are related to some sort to each other. Then there was a question, how does the agent find these classes? And we decided to output all successful experiments that first led to a discovery, let's say, of new class of entangled states with optics. And we found that there are certain blocks that are the same. These blocks can appear in the middle of experiment, at the end, they can appear at the very beginning. It always differs, but there is some similarity. And we decided to output all these most frequent blocks in a table. So let's say ask each individual agent to run the learning process and then output the most frequent block that was used. And we found out that in 11% of the cases, there actually were not many different setups, but in 11% of the cases, this was this kind of interferometer that was used. And our colleagues in Vienna immediately told us that this is a parity sorter. If we plug in a single photon instead of SPDC, we plug in just a single photon and there will be a vacuum plugged in here, then this interferometer will sort out parities of orbital angular momentum, which is a very useful tool as the agent showed us. And the second thing, we were quite puzzled because this one didn't look as something we can explain easily in words. But later, after several months of more understanding, we found out that it is actually also a parity sorter. But we have to look at Klitschko wavefront picture to realize that if we revert this path, these arrows down to the beam splitter, reflect from a SPDC source over here as mirrors, this would be the setup B looks exactly the same as setup A. So these two setups actually operationally very much doing the same thing. And the third one was simple setup to increase dimensionality of our photons. Yes, to conclude this part, the agent not only actually reached the target states, found the way to reach entangled states in optics experiments, but also found the way to find simple experiments with a short length, and also these three settings, which are universally useful in this type of experiments, this kind of interferometers. Now I'm switching to the second example of reinforcement learning designing photonic experiments, and this would be about learning to violate Basel inequality, the topic we are working on in Basel with Nicola and Pavel, who is now here. You probably all know this setup where we have a state preparation device, which could, let's say, produce some bell pairs, try to produce a bell pair, and then we share this pair between Alice and Bob. And what Alice and Bob are doing, they choose randomly one of the two settings, A0 and 1 for Alice, or B0, B1 for Bob. By choosing this, they also get some measurement outcomes, which could be plus or minus 1. And what they do by repeating this experiment many, many times, they try to estimate the probabilities of getting outcomes. Plus 1, plus 1 given A0, B0, plus 1, minus 1 given A0, B0, and so on. There will be 16 probabilities. And by grouping these probabilities into this formula, we get so-called a CHSH value, which we know if it is that it has to be smaller or equal than 2 if our experiment is described by a local model. But if it is larger than 2, then we must have some quantum states that is shared between Alice and Bob. And what we are trying to do, we try to maximize this quantity, this beta quantity, to get a better violation of the CHSH inequality. And this improvement of increasing beta is very much important for implementing device-independent quantum key distribution, or in principle, any other, it's important for any other device-independent applications. So important thing to note here in this picture that we can obtain immediately better values of beta up to 2 square root of 2 by post-selecting, by Alice and Bob post-selecting their outcomes. But this is not a way to go for loophole-free bell tests and for device-independent applications where we have to store all the outcomes that happen with Alice and Bob. And this makes much more challenging achieving high values of the violation. So what's the way to actually improve this violation, improve the beta? We can think of one way, and this one way to write down a general Bogoliubov transformation on n bosonic modes, which would consist of linear optics term, single mode squeezers, linear optics term displacements, and which would correspond to a most general picture, which looks like that. And then try to first decompose this U, V, W into linear optical elements, beam splitters, and phase shifters, and then optimize the parameters of all of these elements, which scale as n squared, where n is the number of modes we have. And by optimizing these parameters of these elements, we try to achieve better violations. But this turned out to be quite hard, even if we limit ourselves to 3 modes. So for 3 modes, I believe we have 23 optical elements, single mode squeezers, beam splitters, phase shifters, and displacements and measurement devices. Then just optimizing them doesn't lead to anything better than was known before. So this is quite challenging. Plus, we're not quite happy with the fact that we use n squared optical elements, because in principle, we might use significantly less. There's no guarantee that this kind of setup in length is the optimal one. Maybe we can simplify it a lot. So to do this, again, we ask our reinforcement learning agent for help. The agent placed here adds additional optical elements to the current table. It gets the current setup that's on the table. Then the setup which agent built, this configuration, is actually used to compute the CHSH value. And then there comes the simulate annealing part. This optimization step where the algorithm tries to actually change the parameters of the elements on this setup to achieve a better CHSH value. And this is repeated in this type of a loop. The simulate annealing tries to improve on the parameters, and then comes the agent again. If the improvement leads to some CHSH value which is better than it was before, agent gets a reward. So this was a good move that agent placed an optical element, because it led to a better value. And then by this process, we try to improve on the values. So first, we tried to take a well-known experiment. This consists of a SPDC crystal, a 2-mode squeezing operation, which gives us photon pairs which are then shared between Alice and Bob. They do some displacement operations, and then they measure the statistics, the outcome statistics. What we found out that the algorithm for this fixed set achieves the best theoretically known CHSH value. So with trials, with time, it improves the value and reaches this dash line, which is a theoretically known line. So we know that for very simple cases, our optimization, our simulated medium works very well. And then after that, we go to an unknown territory where we don't know if we can achieve something better or not. So this is what we get. Typical learning curves we get. This is time, and then this CHSH value improves, and the length of experiment it goes down, and then goes up again because of more complex arrangements. And the experiment at the bottom shows us most frequent setup we observed from this learning curve. So it's quite simple, and it corresponds to a single photon experiment on a beam splitter. So you can think of this as a photon pair, let's say, generator, which conditioned on a click. So we know that in this mode we have photons, they are split between Alice and Bob, and then they do their displacement operation. And the way agent built this setup is by taking actions from this alphabet. This is shown on the left hand side, the corresponding operation. So we went a step further and added the maximum number of possibilities we can for the agent to operate with. And this is the animation that shows successful experiments agent was working with. So you see that for some time, agent maybe is working with the same experiment, adding a couple of elements, but then once in a while it changes completely, starts from scratch. So it's a combination of exploration and exploitation process that happens with the reinforcement learning. And then after some time, you can see that this CHSH value grows. And I think it will stop at 2.71 with this setup. If we take a different agent, this would be a completely different learning process. It will have a different life. That's how it looks. It starts with a simple experiment with the two-mode squeezing shared with this pair shared between Alice and Bob, but then it tries to come up with something more complex to increase the violation. And then we can see this single photon experiment popped up, where these photons are shared between Alice and Bob, and then there's something more complex which is harder to understand happens. Yeah, so I grouped, I just took here two settings from two previous animations, this setting A and B, and the corresponding CHSH values. They are already larger, both of them are already larger than whatever we know from before. So we didn't know that these values are possible to achieve with this photonic experiment. And then what we decided to check if it holds to be good for some different detector efficiencies. So let's say we lose photons before they come to these detectors, to all of these detectors. And this is what we plot here, detector efficiency, which is from 65 to over 65 to 1, and the corresponding CHSH value. And these two curves, this one and that one, these are two known setups, two known before, and we thought initially that it would be cool if the agent actually finds something which takes advantages of both of them. So like at low losses, it behaves like this one, and at higher losses, it behaves like this. So it's like this triangular that happens here. But in fact, the setups that agent found beat both. So it actually, there's a certain gap between what we knew before and the newly designed experiment. And there's a smaller gap, but for all other detector efficiencies. So this is quite interesting what we observed with the new setup. But let me now finish with photonic experiment and move to a topic of quantum walks. where we design new graphs for for quantum walks. So it's an introductory slide that shows the difference between classical and quantum walks. This thing is called a Galton board. We have particles that drop on these nails, or on this on these circles, and then with some probability, with probability 1/2, it can go to the left or to the right, and then it is just a random process that leads to this ball dropping into this basket. And if we drop many balls, we can see that there's a certain distribution. There's a Gaussian distribution of this particle that ended up at the bottom of the Galton board. If we now think of a quantum Galton board, which allows our particles to jump both to the left and to the right at the same time, so in a superposition, then we end up and we measure at the bottom, so measure where a particle ended up. We have a different distribution which has peaks far from the origin. The larger the board, the more further away are the peaks that we get from our quantum walk. So let me briefly tell what's the mathematics, the simple mathematics behind this process. We have a graph, like the graph with 8 vertices, and there's a particle, classical particle placed in vertex number 1, and then with probabilities, it can jump to nearest neighbors with probabilities described by matrix T, which is transition matrix. And the whole process that describes the probability, the outcome probability distribution P of T, is obtained by solving this differential equation. In quantum case, on the other hand, we allow our particle to move to the nearest neighbor vertices coherently. And this coherent propagation is described by the Hamiltonian Hj with Ij elements, which correspond to the Ij elements correspond to nearest neighbors that are available for instance 4, 5, 2, 4, but not 4, 6, for instance. And if we look closer, this corresponds, of course, to the adjacency matrix, to the same matrix that was used before in the classical case to obtain the transition matrix. And the final state we're interested in, psi, quantum state, is just obtained by solving the Schrödinger equation. Okay, so what I showed you, this quantum scenario can be studied, of course, by simulating the Hamiltonians that I showed you, the Schrödinger equation. And we see that with time, particle actually, if it looks like this Galton board of infinite length, so it's a long board, we get that the particle propagates linearly with time. So it's called ballistically, so it goes quite far from the origin. But in classical case, it goes quadratically. So it's like a Brownian motion. It moves quite slowly away from the origin on average. And this gap corresponds to this speed up in the particle propagation, some quantum speed up that can be observed in the experiment. For instance, this recent photonic implementation. There are many more implementation of this quantum walk on the line. So the reasonable question to ask, in which situations do we get the speed up? So we can say it's certainly on lines, on cycles, on hypercubes, glue trees, some photosynthetic structures, and some other quite symmetric graphs that we know of. But in most cases, we talk only about propagation of particles between vertices that are far apart. So if there are some boundary conditions, if graph is small, if it's finite, we are not sure anymore that there is any advantage of particle transport. The other thing that we always have dark states. So there are some vertices where quantum particles never appear. So it just happens. It doesn't happen in classical case, but in quantum cases, it's possible. And there are also some practical difficulties. For instance, our measurement apparatus introduces drastic change in dynamics when we measure we disturb the system, and it can lead to a Zeno effect. So if we measure where we wait for our particle, it can happen if we measure too frequently or too strongly. We too strongly couple our measurement apparatus to a target vertex, then we end up not seeing particle at all. And let me give some toy example with 3 vertices that shows that depending where we put our measurement apparatus, we couple it to vertex 2, which is over here, to 2, which is in the middle, or we change the labels. We start in the middle, and here we start at the left edge. And we, depending on which scenario we choose, we always get different results. And only in one of them, it is the case that quantum particle actually reaches the measurement apparatus faster. So it's very much depends. And before we learned that quantum particles are faster on lines, but it's not the case on the small line, because only in 1 case out of 3 we get a faster transport. Then the reasonable question to ask, how to detect when quantum particles are faster. So we're given a graph which we never seen before. How do we find out? And this is important for finding out most efficient graphs for energy transport and for quantum algorithms. So maybe there's some graph out there which is like very asymmetric, but it's perfect to study quantum algorithms or energy transport problems. So how to find out? So to find out, we can model quantum transport on graphs compared to classical transport. And this takes a lot of time because we need to run a lot of simulations because there are so many graphs. It is not possible to cover all the situations. And moreover, we don't get any understanding without additional analysis. We just get an outcome faster or not. There's a possibility to find relations between graphs of interest from known examples. For instance, if we know that this graph is a hypercube, if we attach some edges, we know that the speedup must also happen. But this is rarely possible. And then the third possibility is to do to find intuitive solutions depending on our intuition. For instance, it looks like that maybe coherent propagation of particles in this structure should lead to some constructive interference in this part of a graph. Hence, we might get a speedup. But this is not perfect, just intuition-driven case. So what we decided to do, we decided to use some computer vision systems, essentially convolutional neural networks, to look at our graphs and try to predict if this graph would give a speedup or not. So this convolutional neural network would take a graph configuration, some labeled graph, which corresponds to some adjacency metrics, and then with a certain type of filters, edge-to-edge filters and edge-to-vertex filters, which are learnable with learnable values, it would feed it to a fully connected feed-forward neural network, and then output a decision whether this is like quantum favorable graph or it's classical. So the key here is are these learnable filters. This is how usually the filters work in convolutional neural networks. They take part of a matrix. Let's say these are pixels. Each square would correspond to a pixel, and the number of pixels are taken. They summed up with a certain function, and then this is mapped to a smaller matrix like this. The problem with this kind of filters working for graphs is that there are no immediate nearest neighbor relations between our elements in the adjacency matrix. In this one, if I take a small piece in this adjacency matrix, it actually contains no logic. Why would there be certain relation in this corner? But what became obvious to us, that if we take, instead of nearest neighbor pixels, we take columns and rows like this, then it suddenly makes sense, because each column corresponds to connectivity of a certain vertex. For instance, if we take 1, 1 element, the first row, it corresponds to how is the first vertex connected to all other vertices. For the second row, how the second vertex connected to all the other vertices, and so on. And if we learn how to sum up properly all these columns and rows, then we end up with a matrix of the same dimension. Then we can apply after that a filter which just scans the diagonal, sums up the total connectivity of each vertex, and we end up with the following situation: we scan all these crosses, convolute with this type of matrix, end up with another matrix, and then we sum up with a certain weight the sums of rows and columns on the diagonal, and we get a polynomially smaller number of values, important values. So after we run it, we get the following. So if we test it on small lines, which I showed you before, I showed you like length 3 lines. Now let's take 4, 5, 6, 7. We train on some lines, not all, but some lines. And then we see that the training goes such that the loss on the training set goes down, not to 0, but to some values. And in parallel, the accuracy on new graphs, which were not shown to the agent, to our convolutional neural network, they go to 1 for 4 and 5, and to smaller values to 6 and 7. This is actually not surprising that it doesn't go to 1. The fact is that there are always very individual cases that happen there. So there could be, let's say, a graph which has nothing in common in terms of coherent transport to all other graphs that the network was trained on. So we are quite happy with this over 90% efficiency for even this small graphs with 6, 7 vertices. The other thing that we wanted to test is to train it on small lines, 4 and 5, which gives us this loss in training, but check it on different graphs of different dimensions. So on 6, 7, 8, 9, and 10. And what we found out that actually the accuracy is not 50%, it's larger. So no matter like which of these we choose, the graph is larger, the adjacency matrix is larger. This convolutional neural network never seen graphs of this dimension. Still, it can predict with some probability the result of quantum and classical walk. And this just shows the values in the last layer of neurons. And the curious thing that we found out that the activations of these neurons, some neurons are quite symmetric. So for instance, you see that this part is almost the same as all other parts, and the same for different neural network size and for different graph size is the case. We have some symmetry, and this is due to the fact that actually neural network learned that some graphs are isomorphic to each other. So it's no matter how we label certain vertices here, we can exchange 4, 5. It will not affect transport in any way. So this is kind of was automatically captured by the neural network. So then we decided to jump on much more complex cases. We decided, okay, what we now test if we now test it on random graphs. So the whole range of possibilities we can imagine. And there are many of them. For instance, if we take graphs with, so this is number of vertices, n, and this is number of graphs. If we take, I assume, let's say 30, which is reasonable like size, 30 vertices, we get around 2 to the 300 different graphs, which is of course impossible to train on all of them or simulate all of them or simulate even a small fraction of them. It's very complex. But we simulated only 1,000 for training. So, and what we hope for, we hope to see any sign of generalization capability. And so this is an example. This is how this two examples from the test set. And we ask the question like, what happens here? So this is what we found out. We found out that for different sizes, 15, 20, 25, we get almost the same performance. So it's not very much dependent, simply because maybe the space is too large. It makes not much difference whether you have 15, 20, or 30 vertices. The space is enormous anyway. And we computed recall and precision functions. What are these functions? So let me, to finish with this result, let me look at the picture of true positive and true negative outcomes. Let's say we have this space, and this part corresponds to graphs that are quantum, can show quantum speedup. And this graph corresponds to the ones that cannot show it. Let me call it, just for simplicity, quantum graphs. These are quantum graphs. What our predictor actually does, it correctly classifies this region, graphs from this region, but falsely classifies graphs in this region. So these are false negatives. So it attributes classical class to this one, but it's actually quantum class, and it falsely attributes this region to quantum class, however it's classical class. So what we want to do, we want to minimize this area. What happens in our particular case, that these two regions are not equal. We have many more. We have actually 90% of classical graphs compared to quantum graphs. And yes, and if we just decide to simulate without using a neural net, we decide to simulate all these graphs, what we end up with 10% correctly guessing that it's a quantum graph, and 90% case will be incorrect about our guess. And what we are of course interested, we need to improve this number. We need to go from 10 to some higher number. What we ended up with the numbers that I showed you on the previous slide, that we moved this 10% towards 30%. So instead of simulating 10 graphs and getting just one, which is will be quantum enhanced in the end, we need to simulate only 3 of them on average. This is like three times improvement. Yes, so this slide summarizes this result. Before we had 10% guess for quantum class, 90% guess for classical class. With neural network, we ended up 30% guess for quantum at 93% for classical. So we improved both of these guesses. The next step, which was quite reasonable, is to include losses in the system, because now once we want to improve to actually go to real experiment, we need to take into account how the losses affect our prediction capabilities. And we looked at these types of master equations, and again trained the neural network with a very similar scheme which I showed you before. Again, on graphs, we trained on one set of graphs, we tested on graphs which were not shown before, also of sizes which were not shown before. And this is what we got. We got that it's actually on cycle graphs, it was very positive outcome, that the accuracy goes to 1, losses goes to 0, and transfer efficiency of transport matches very well with actual theory, which we simulated. With this, I'm at the end. I told you 2 stories. The first one was about creative designs of experiments produced by reinforcement learning agents. And the second part was about quantum transport advantage, like quantum walks, and for prediction with neural networks. So with this, I thank you for your attention.
Thank you for your talk. So please, questions. If you want to ask something, please raise your hand in Zoom. So any questions, please? Okay, Stanislav, please.
Okay, let me try. So are there any simple features of these random graphs which you found out corresponding to those which perform better for quantum walks or for classical walks? Something, I don't know, some simple properties?
So it was actually very hard to analyze this to find out what actually happened. We only managed, I must say, we only managed to answer this question for simple graphs. So when graphs are of reasonable dimension up to 7, so these are, let's say, line graphs. What we found out by looking at the activations of neurons, that neural network doesn't like if initial vertex is directly connected to a target vertex. There's a very high negative vote. So these red bars, they actually, most of them, I believe, they correspond to connectivity of initial vertex with a target, they correspond to connectivities of initial vertex with other vertices. So it doesn't like when initial vertex is very much connected with a graph. So if it is the case, then it seems it's quite easy for classical particle to reach target vertex if they are very close to each other. And this holds for all sizes that we saw. So these red bars are quite high. But it is the case that neural network also likes if the target vertex is well connected to the rest of the graph. So it's good that it's bad that the initial vertex is very much connected, but it's good if the target vertex is well connected. So, and we see it from the activations of the neurons. But this is derived only from small graphs. So I cannot say if it's true for larger graphs, but I see no reason why not. Maybe it's also helpful.
Okay. Dr. Xiaosuan Ma, please.
Okay, thank you, Alexey, for this very nice talk. So I have several questions. The first one is, in the first part of your talk, you mentioned about the length of the experiment. How do you define that parameter?
So the length is defined as the total number of elements the agent used in constructing the setup. So if agent plays, let's say, beam splitter, hologram, one more beam splitter, then the total number of actions will be 3, and the length of experiment will be also 3. And this is, of course, a simplified story. If you go to the lab and try to implement this experiment that agent designed, of course, there will be an overhead of more elements because you would need to do some additional alignment. You will need to balance your interferometer. This will, of course, lead to additional cost, which was not studied, but this is like the first step to give you the minimalistic scheme so that you can additionally study it with in your lab and actually implement more complex experiment. But the rule of thumb is that the simpler the agent finds experiment, it's most probably the simpler you will get implementation in your lab.
Sure. So in your talk, you mentioned sometimes one step, so step 1 can have several elements, and step 3 can have less elements comparing to step 1 because of the cancellation of some components. Do you consider that, or do you include that scenario?
We consider only after simplification. So you're right that agent can do in principle many actions, but it can end up in the empty table. We count the final.
Okay. And the second question is about the learning process. You mentioned that if you give your agent some training for simplified states, for example, you talked about these 332 states, and after training with these 332 states, and if you give the agent of a task for training for 333 states, and it will have a much faster convergence. Can you give us some, for example, the physical understanding of this speed up? Where does it come from?
It actually, we understand more or less this example. We don't understand many examples, but this one comes from the fact that in both 332 and 333 experiments, an interferometer like this is used. So, and it was easy to kind of learn it if the target is 332, but if the target is 333, it was quite complex for the agent to find out that this block is needed, because to create 333, in addition to this block, you need several more elements. And agent just struggled to realize that this kind of interferometer is needed to be built. But if you need a 332, it's actually very straightforward with this setup to build a 332 entangled state. Or with that setup, so because they are more included, yes.
So is it fair to say that if you include such a structure, this parity sorter in your program, that's as an entity, it will simplify the program for finding more complicated states?
It will. So it's known because it is the way automated approach works. The automated approach that was designed by Mario, right? So this is certainly works. So this is this red lines that we have here. But the problem is it seems to be not enough. So there is some other process that happens, not only adding these new tools, but also something else, because there's a huge gap between these two. And this something else maybe corresponds to simplifying the experiments, because agent internally tries to get as much reward as possible per step. That automatically means that you favor shorter experiments. Maybe agent simplifies just shorter tools, just smaller experiments that it can use. Maybe there is something more to that, but we see that there is a gap between these two.
Okay. And my last question is about the graph part. Have you considered the directed graph in your program?
No, it was
meaning
all
there's a weight between both between two vertices.
It will be interesting, because in classical case you can easily model that, because you can construct a transition matrix which is not symmetric. So Tij is equal to Tgi for indirected graphs. For directed they will not. But for classical case, of course, we need our Hamiltonian to be Hermitian. So it will lead to an overhead, to polynomial overhead of implementing a directed quantum walk. Which is very interesting to do, but it's of course next more complex step. But for neural network, importantly, it does matter. Of course, the neural network is designed such that it works with graphs, and in principle it works with adjacency matrix. In principle, it doesn't care what numbers do you put here. So it should also work for asymmetric adjacency matrices. It's only a question: how would you train? How would you efficiently train your network with examples?
And why do you say it's a polynomial overhead if you consider directed graph?
I know of a Szegedy type quantum walk construction, which works for directed graph, and it has a polynomial overhead. But to think of maybe logically, if I look at this Hamiltonian, at this, for instance, vertex, I need to come up with a unitary operation which contains jumps to node 7, 3, and 4. And there will be a different unitary operation that contains a different element from jumping from 4 to 1. So it's kind of you're doubling your representation. So you cannot just encode both into one. So you kind of have to split into two. So you need kind of a coin which tells you in which direction.
Direction,
yeah,
yeah.
But something more. Yes. So it needs to.
Right. Another, by the way, I would just like to comment that another way to deal with this situation to avoid the coin might be use adjust your Hamiltonian such it's not Hermitian. As you probably know, that there are a lot of this pseudo-Hermitian or PT symmetrical system or theory developed in the recent years.
Yeah.
Maybe one
so
can...
what is interesting to us, to Alex and Leonid and myself, is to look at these cases where there are additional phases. So edges have phases. So the Hamiltonian is still Hermitian, right? But we have a different. The probability to go from 1 to 4 is the same that from 4 to 1, but there's a different phase.
That's so also one.
And this is quite exciting because with these phases, we can guide our particle in different regions of the graph. And this is potentially exciting, I must say, to realize maybe the set of best graphs where the phases are such that they will enhance our transport. But this is the future of our research. I think we will study the situation. So the only change that will happen for this asymmetric PT asymmetric graphs that we add complex numbers in this table. So there will be not 0 and 1, but there will be some complex value for it. But it's not a directed kind of the full directed quantum walk because the probabilities will stay the same anyway.
Right. Okay, thank you.
Thanks for the question.
Okay, Alexander Elzhans.
Yeah, thank you very much, Konstantin. Alexey, thanks for your talk. It is I think, very dense, but I have a question to the second part of your talk related to the, I call it Tserilson theorem. So can you show me some pictures? Yes, about that. So my question is following. So in your case, you consider completely unitary transformations. So of course, if you use unitary transformations, only unitary transformations, you can build up some network or some kind of efficient scheme how you can maximally violate Bell inequality. But the question is, if you have some decoherence in the setup, and in this case, it is so. Is it possible to introduce decoherence in some small elements of this setup, and in this case, optimize this setup? Because no, of course, if you use, for example, 5 some equipment tools or 2 equipment tools, practically it is very big difference. So I mean, decoherence should destroy your results. What do you think about that?
It's a very important question for us, and it highlights advantage of our approach. Because as you see from the scheme, agent in principle doesn't care of noise. So what the agent does is just an algorithm which places elements from a toolbox. And in this simulation, there can be losses, noises, and other undesired processes. And this is all taken care in the simulation part. And the agent would try to adjust itself and place different elements depending on how the simulator behaves. So what we tested as the first step, we tested the situation where detectors are lossy. So for instance, before it clicks, we know that some portion of photons, they were lost. And this corresponds to the detector efficiency. So if it's not 1, that means each detector lost photons with some probability. And of course, if we lose photons, we get lower CHSH value. And we see that the setups, although the agent was only working with this value, with detection efficiency 1, the setups that agent designed, they work quite well for other detection efficiencies. And the thing that we are trying to explore now together with Pavel is to see if we fix different detection efficiency now, will we get some other setup? Maybe there's some other setup which gives even better CHSH value. So this is potential. This is an advantage of the approach, that it doesn't really care about if it's lossy or not.
Yeah. Okay. Thank you. So thank you very much. So.
Oops. Maybe I didn't get. So usually when we try to check Bell inequalities, we have some post-selection of the number of counts. I mean the total number of detectors which click. So usually detector efficiency doesn't change the value. So could you explain better maybe?
So here in the studies that we did, we do not do any post-selection. The reason we don't want to do post-selection is because of device-independent applications. If you now decide what events to count and what events not to count, then you open the door to certain loopholes or to certain attacks. And if you count all the events, then you kind of close this door to the situations, right?
Okay.
And,
okay.
I can imagine if you post select that, maybe detection your inefficiency just influences the rate with which you obtain your good values, your good CHSH values. But here it actually influences the value itself.
Okay, I get it. Okay, Ranjit, please.
Thank you for your interesting talk. I have questions related with your first part of the presentation. So the first question is, am I right to model such simulations? You have to model all feasible actions of each optical element and combinations between each optical elements. Am I right?
You mean this part, the CHSH, Bell inequality part, or?
Yes, first part of your presentation.
First part. Mm-hmm.
Yeah. Am I right?
Yes, whenever agent does an additional action, experiment changes, so you model it again.
Okay.
In the loop. So for whatever, if I show some learning example.
So you have in advance you have to model all the combinations, possible actions.
Not in advance, because for instance, look at this timeline from 0 to 10,000. So experiment 1 would correspond to placing one element, and you model this element. And then you place the second element, you model now the combination, but you kind of, once you finish with your experiment, you forget what happened before because you start from scratch. Mm-hmm. So it's not the case that you model all the combination which agent suggested. Mm-hmm. Mm-hmm. Not that are theoretically possible, because if I look at all possibilities, it's something like there's some huge number. Yes, I don't have
45,000. Yeah. Okay.
No, 45,000 is just a tiny sample. I think it's around 10 to the 17 possible experiments that we can reach. It's 45,000 is a really tiny set.
Mm-hmm. Okay. Second question: what software and machine hardware you are using to simulate such experiments?
So we So each of these three projects is different in the way it was implemented, but the general scheme is that we program machine learning ourselves because we use our own projective simulation model, which was developed in Innsbruck. We spent years on developing this physics-inspired approach. And it's written in Python, it's like a package, and it runs only on CPUs. So we don't have a GPU-enabled parallelization capability yet, at least. So it's we run it on CPUs, and each individual agent is one CPU. You can think of this one run as one CPU, but you can run multiple agents at the same time if you have multiple CPUs. So in practice, we have computational clusters with sometimes up to 1,000 CPUs available. So you can run 1,000 agents at the same time in parallel and then look how at the statistics, how much different they are and so on.
Thank you.
Pavel, please.
Yeah, thank you, Konstantin. Alexey, another question came up to my mind when I was listening to your talk. It's about the first part as well. So when you have this, when you think about this possible setups of a given lens, yes, all possible optical tables, naively you would say just some binary tree kind of graph, right? You can add a new element from your alphabet at every step. But then you said that your exploration space is a scale-free network.
Yes.
So I was wondering whether you can explain how it ends up being a scale-free network. Thank you.
That's very interesting. So initially we were surprised in the first project, like why it learns that well. So maybe like the exploration space resembles some maze, and that helps because there are many ways to reach the same target state, and the agent just finds one shortest path. If it were a binary tree, initially we thought it would be bad, but actually reinforcement learning would also work for a binary tree. So it's not that it's you know, a failure if you apply reinforcement learning to binary tree exploration space, because there still could be the case that your experiments that you're interested in are located in the same branch. So this would correspond, leaves will be uncorrelated, but they could come from the same branch. And it could be that if you learn to which branch to go, you automatically learn to find good leads in this tree. But it seems that if your exploration space is more complex than just a binary tree, then agent can be more efficient. But this is just, yeah, from observations. And in our project together with you, right, we also don't have a tree. We have, because of displacements, you can add additional displacements, but they do not are implemented. So you kind of stay at the same space, but maybe you don't go back. I'm not sure, but it's probably not exactly the binary tree, but it's much closer to binary tree than it was with the scale-free network in the previous, in the first example I gave. And why it is scale-free, I don't know actually. So we just checked the parameters. It turned out to be scale-free, but it's not clear why it is scale-free.
Okay, so at the end, I think we have a question from the chat from Nikolai Skrябin. Does the graph class depend on the initial vertex?
And is this question to which part of the talk, graph class in quantum walks or in exploration space? Or okay, maybe I answer both questions. What, sir?
I guess it was the last one, the quantum walks.
The graph class. Yes, so if it's quantum or classical. Yes, it depends a lot, because in the example, in the toy example that I gave, with 3 vertices, the start vertex was always 1. So for instance, this blue one is here 1, and here it was in the middle. And we see that the dynamics of gray and blue, they are different. So we get different class. If it's blue, there's a speed up. If it's gray, there's no speed up. So it for sure depends. And moreover, if it's, let's say, here 1 placed at, and we detect in 2, then we have a quantum xenotype slowdown, because we measure at the vertex which is very close to initial vertex, and we see that it's quite significantly slower compared to the classical case, which is super fast.
Okay, so I think it's time. Thank you very much for your talk. It was very interesting, and see you again in our webinars if you want.
Yes, thank you for invitation and for your questions.
Yes, and again, I would like to repeat the announcement. So the next week we will have a talk from Ivan Dyakonov, and it will be about just a moment, a linear optical platform for quantum computing in Moscow State University Quantum Technology Center. So you are welcome next week. See you all.
Thank you. Bye.
Thank you. See you next time.
See you.
See you. Bye-bye. Thank you.
Bye.
До свидания.